So, good morning, everyone. So now our first speaker for today's morning section is Professor Sebastian Heller, and he is going to speak on higher solutions of Hitching self-duality equations and real sections of Deligne-Hitchin moduli space.
So, thank you for the introduction, and thank the organizers for the invitation to this fantastic place here. So actually, I will only say a few words about these higher solutions of the self-duality equation, and I will focus on general properties of real sections of the Deligne-Hitchin moduli space and its relation to harmonic maps. So for that purpose, I would like to introduce the Deligne-Hitchin moduli space via the self-duality equation approach. So let me start recalling some basic facts about Hitchin self-duality equations. I consider them in the most basic setup. So I restrict myself to a rank 2 bundle, trivial rank 2 bundle over a compact Riemann surface, usually of a genus greater or equal than 0. And here I have a unitary connection and a so-called Higgs field, so a complex linear differential which takes values in the trace via endomorphisms. And the unitary connection and the Higgs field are coupled by these two equations. So the Higgs field should be homomorphic in a certain sense, and the unitary connection has curvature, which is basically given by the Higgs field with its adjoint with respect to the unitary metric on our rank 2 bundle. So because I want to relate my sections of the Deligne-Hitchin moduli space to harmonic maps later on, it's always good to have some examples in mind. And one of the most important examples is maybe the classical example of uniformization. So I start with a compact Riemann surface of genus greater or equal than 2, and I take a metric of constant curvature -4 and a spin bundle on that surface. And then the metric defines a Levi-Civita connection, and this induces a unitary connection on the spin bundle. And this unitary or Hermitian metric is denoted by nabla S. And if we do that, we can also write down a nice Higgs field on the direct sum of the spin bundle plus its dual, which is of the following form. So what 0 is should be clear, and the 1 in the lower left entry just means that it's a one form from with values in the homomorphisms from S to S dual, so in element in S to the -2. So it's just a section in the trivial holomorphic line bundle, and I normalize it to be 1. And then it's a easy computation done by Hitchin that this is actually a solution of Hitchin's self-duality equation. So I'm not only interested in some particular solutions, but also in the whole space of solutions. And it turns out that the space, or rather the moduli space of solutions has a nice structure. How to go to the moduli space? So we have a nice action here by the unitary gauge transformations on the space of solutions. So if we start with a solution and gauge it, respectively, we conjugate the Higgs field, we obtain a new solution of the self-duality equation, which can be, of course, very easily be computed. If we do that, we expect to have a moduli space, perhaps only if we restrict to nice points, and these nice points are corresponding to irreducible solutions. What does it mean to be an irreducible solution? It just means that the connection and the Higgs field do not leave any proper subbundle invariant. So if this is the case, so if there are no invariant subbundles, we say we have an irreducible solution. And then it turns out that the moduli space, so the space of irreducible solutions of the self-duality equations, modulo this gauge transformations, is a nice smooth manifold of finite dimension, namely dimension 12G minus 12, where G is the genus of the Riemann surface. So of course this is a classical theorem from 30 years ago. But these moduli spaces still play an important role, in particular because they are equipped with very rich geometric structures. And yeah, one of the most important structures is the so-called hyper-Kahler metric. In general, a hyper-Kahler structure on a Riemannian or on a manifold is given by a Riemannian metric G, which is scalar for three anti-commuting complex structures I, J, and K, which satisfy the quaternionic relations. So I times J should be K. So in the case of the Hitchin self-duality moduli space, the Riemannian metric is given as follows. So if we work on the infinite dimensional space of solutions, we can easily write down an L2 metric, and then it's not too hard to compute that this is actually well defined on the quotient if we restrict to irreducible points. So this is the Riemannian metric. What about the complex structures I, J, and K? So the complex structure I can be best described by using the notion of Higgs fields, which is of course well known to most or all of you. But let me briefly recall that. So a Higgs pair or Higgs bundle consists of a holomorphic vector bundle given by a holomorphic structure, and a holomorphic, in our case here, holomorphic traceless endomorphism valued one form, phi, the so-called Higgs field. If we start with a solution of the self-duality equation, of course we have the forgetful map. So if we forget about the 1-0 part of the connection, and if you forget about the Hermitian metric in the background, we just have a Higgs pair, which still satisfies this holomorphicity condition. If we want to produce moduli spaces, it's a good idea to introduce the notion of stability. And for Higgs pairs, it just means that a Higgs pair should not admit any invariant holomorphic line subbundles in our situation. I restrict to the rank 2 case. So it should not admit any invariant line subbundles of non-negative degree. And then, as a nice example or important fact, if we start with an irreducible solution of the self-duality equations, the corresponding Higgs pair is automatically stable. So this is computed by some easy Weizenberg argument. But it turns out that the converse is also true. So this is an important result of Hitching. Namely, if we start with a stable Higgs pair, this gives rise to an irreducible solution of a self-duality equation, and this solution is unique up to the action of the unitary gauge group. So this is the way to obtain a complex structure I, namely the moduli space of Higgs bundles is complex. Natural complex analytic variety in the following way. So we have a complexified gauge group acting on the space of stable Higgs pairs, and then the quotient denoted by the Dolbeault moduli space is a complex manifold of dimension 6g minus 6, and by the result of Hitchin we have an identification as real manifolds of the Dolbeault moduli space with the moduli space of solutions of the self-duality equations, and we can use that to obtain a complex structure I on that moduli space. So a particular nice example, which of course was also noted by Hitchin, is the following. If we restrict to the complex submanifold given by restricting the Higgs field to be 0, we obtain back the famous Narasimhan-Seshadri theorem, namely the stable Higgs pairs with 0 Higgs field are just stable holomorphic bundles, and they correspond to irreducible unitary connections. by Benaro-Schiman's theorem, but in that setup it also follows. Okay, that was the complex structure I. There's also the complex structure J, which I want to explain how it is given. And for that, we do the following. We start with a solution of the self-duality equation, and we consider the following connection, NABLAB, plus the Higgs field, plus its adjoint. And then due to the self-duality equations, this connection is automatically flat. And if the solution was irreducible, this connection is also irreducible. And then a theorem of Donaldson, also from '87, tells us that every irreducible flat connection is given in that way. So we get an identification of the moduli space of solutions of the self-duality equations with the moduli space of irreducible flat connections, the de Rham moduli space, which has a complex structure J from the complex group SL2C in our case. Okay, if we already have that connection here, I can explain a link to a harmonic map theory. So if we look at that connection and take a parallel frame, of course this is only well defined on the universal covering. So we can consider the adjoint times the frame, and this is a map into the space of symmetric SL2C matrices. And as such, it's a harmonic map. But the later space is basically two copies of the hyperbolic free space if we use the quadratic form minus the determinant. So in that way, we get from solutions of the self-duality equations automatically equivariant harmonic maps into the hyperbolic free space. And in fact, it was this observation that solutions of the self-duality equations are related to harmonic maps, which was used by Donaldson in order to prove his results. So he started with a section and applied the harmonic map flow in order to prove that one gets in the end a solution of a self-duality equation out of a connection with a given representation. If we go back to the example in the beginning, so if we apply that procedure here to the solution of the self-duality equations corresponding to uniformization, what we get is simply the developing map of a hyperbolic metric, which sits inside the hyperbolic disk inside hyperbolic free space. So this is a particular nice example here. So altogether, what Hitching has proven is that this, the moduli space of solutions of the self-duality equations with the L2 metric I explained before, and with these three complex structures is actually a hyper-Kahler manifold. And of course, this space has a lot of more structures, namely if we restrict to the complex structure I and take a corresponding holomorphic symplectic form given by the Kahler forms with respect to J and K, then it turns out to be a very nice integrable system by taking the determinant of the Higgs field, so just taking phi to the determinant of phi, which is of course in our situation a homomorphic quadratic differential, and this is the famous Hitchin system here. Okay, let me skip that. So I'm very much interested in this Deligne-Hitchin moduli space, and one reason for that is the twistor space of the moduli space of self-duality equations. So what is a twistor space of a hyper-Kahler manifold? The idea behind that is that one wants to encode all the data of a hyper-Kahler manifold in terms of complex geometric data. And this works as follows. So one starts with the hyper-Kahler manifold M and takes the topological product with the round 2 sphere. And one defines a natural, almost complex structure by taking the complex structure parameterized by the point in the two-sphere on the first factor, and the natural complex structure by rotating around 90 degrees or identifying S2 with CP1 on the second component. And the fact that we have started with a hyper-Kahler manifold implies that this almost complex structure is actually integrable. So what we get is a complex manifold, the twistor space, and this automatically has a complex or a holomorphic projection to the second factor, because the complex structure on the second factor does not depend on the point of in the first factor. So this is holomorphic, and the fibers are of course identified with the manifold M equipped with the corresponding complex structure parameterized by the point in the two-sphere. We also have a real involution on that manifold, just given by taking a point and a point in S2 identified with CP1 and mapping it to the same point and the antibodal point, namely in the identification with CP1, we take minus lambda bar inverse. And because this means that the complex or the complex structure on the first part is just mapped to its inverse, it's actually a real involution of that complex manifold. And then it was shown by Hitching and some of his collaborators that M and its geometry can be recovered from that twistor space. So, for example, the manifold is given by a component of the space of row invariant holomorphic sections, namely exactly these sections which are of that very simple form with respect to that trivialization here. And this twistor space carries some kind of additional structure. It has some kind of holomorphic two form, which encodes the Riemann metric G and also the other complex structures on that space. What makes the case of the Hitchin moduli space so interesting is that there's another description which just uses complex geometry. So there's a different description of that moduli, of that twistor space, which just uses complex geometry. And this was pointed out by Deligne. And the idea behind that is that one wants to interpolate between the Higgs pair picture of a solution and the flat connection point of view, giving the complex structure J. And this works via the so-called associated family of flat connections. So one not only has one flat connection if one starts with a solution of a self-equation, but a whole C-star family of flat connections, just by taking the unitary connection and adding the Higgs field and its adjoint scaled by a spectral parameter in that way here. Okay, so how does this really work? So let me start with a definition due to Deligne and or Simpson. So a lambda connection for some complex number lambda is given by a holomorphic structure on a vector bundle and a first order differential operator D, which satisfies two conditions. So the first tells us what kind of differential operator this is. So it satisfies some kind of generalized Leibniz rule, where in that formula I just take the decomposition of the exterior derivative or of the derivative of functions into complex linear and complex antilinear parts. So it takes a complex linear part here and scales it by lambda plus f times ds. And there's an additional integrability condition which basically tells us that D is holomorphic or something like that. So let me give some kind of examples for that. If we restrict to the case lambda is 0, the first equation tells us that we just have a tensorial field. So it's just a complex linear one form. And the second equation then tells us that this is actually holomorphic. So what we obtain is a Higgs pair. If lambda is 1, we can just add the holomorphic structure and this operator D in order to obtain a flat connection due to the second equation. So it's a connection because of the first equation, and it's flat because of the second equation. And for general lambdas which are not 0, we have to add del bar plus 1 over lambda D in order to obtain a flat connection. Then we also have that the complex gauge group acts on the space of lambda connections. And if we again restrict to stable or irreducible lambda connections, we obtain a complex manifold now of dimension 6G minus 5, which is automatically fibered over the complex line. And its fibers are either isomorphic to the Dolbeau moduli space of Higgs bundles if lambda is 0, or they are isomorphic to the Dirac moduli space if lambda is not 0 by the above example. In order to get to the twistor space, we also have to add some kind of point at infinity. And because this corresponds to the complex structure minus I on the Hitchin moduli space, this corresponds to anti-Higgs fields, so Higgs fields on the complex conjugate surface. So let me denote by x bar the complex conjugate surface of our starting Riemann surface. And what we can do then is we define a map on lambda connections. So we have a lambda connection with triple, which gives us a lambda connection on our Riemann surface X, and we map it to a lambda connection, 1 over lambda connection on the Riemann surface X bar. So you have just to look at the definition in order to see that this really gives a holomorphic structure on our complex conjugate Riemann surface, and this is a 1 over lambda connection with respect to the complex conjugate surface. Okay, this map psi is compatible with the gauge group action, and therefore it gives us a biholomorphism between the Hodge moduli space of lambda connections when restricted to the punctured plane to the Hodge moduli space of a complex conjugate Riemann surface. And no, lambda is complex in here, or no, lambda is a complex number. In that computation, lambda is a complex number, which is so it works for all complex numbers. This isomorphism works for all complex numbers except 0. Okay. If we do that, we see from that formula here that this isomorphism is covering the map lambda goes to 1 over lambda. So what we can do is we can obtain the Deligne-Hitchin moduli space by gluing these two copies via this biholomorphism psi. And if we do that, we automatically get a covering to CP1 by just, if we are in the first component, we map to lambda, or if we are in the second component, we map to 1 over lambda. And this is, of course, compatible because of that definition. So this is the so-called Deligne-Hitchin moduli space. And in order to describe it as a twistor space of solution of the self-duality equations, I first need to point out that there are some natural automorphisms. So for any t in the multiplicative group, we obtain the action on lambda connections as follows. We just scale lambda, and we scale the holomorphic or the first order differential operator in order to obtain a new lambda connection. And this action is already contained in Hitchin's paper on self-duality equations, where he computes that there's a C star action on the moduli space of solutions of a self-duality equation. So for t is -1, we just denote this automorphism by n. And there's another important automorphism, which I denote by C for complex conjugation, by just complex conjugating everything. So I just complex conjugate lambda, I complex conjugate the holomorphic structure on X to get a holomorphic structure on X bar. And if I say complex conjugation of a holomorphic structure, I just mean I conjugate or I gauge this holomorphic structure with the complex conjugation on my trivial rank 2 bundle C2, and this then gives me actually a holomorphic structure on X bar, and then D bar is naturally the first order differential operator satisfying the conditions of a lambda connection on the surface X bar. So if we compare N and C, it turns out that those two actions commute, and they give rise to an anti-holomorphic involution of the Deligne-Hitchin moduli space, which then covers the involution lambda goes to minus lambda bar inverse, so the antipodal involution of CP1. Okay, and in that framework, what was obtained by Deligne and described by Simpson is the following, namely this Deligne-Hitchin moduli space as a fibration over CP1 is isomorphic to the twistor space of the moduli space of solutions of the self-duality equations in such a way that the natural anti-holomorphic structure rho on the moduli space of self-duality equations is given by this product C times N, and such that the real sections corresponding to solutions of the self-duality equations, so in the identification P is M as D times S2 or times CP1, these sections correspond to lambda maps to P comma lambda. So in this identification with the Deligne-Hitchin moduli space, these sections look at, or are given as follows. Lambda is mapped to lambda, and then the lambda connection given by del bar nabla plus lambda phi star and lambda del nabla plus phi, which is basically exactly the same thing as this associated family of flat connections, but in the language of lambda connections. Okay, so what we get from that is a very nice description of the twistor space. So the twistor space is obtained by the space of solutions of this highly complicated self-duality equations. But we have a complex analytic description, and this doesn't use any kind of knowledge about the solutions of the self-duality equations. So it's very natural to ask if we can use that description of the Deligne-Hitchin moduli space in order to reconstruct the twistor lines, or in order to reconstruct all the solutions of the self-duality equations from a complex geometric point of view. And actually, this question was asked by Simpson about 20 years ago in the following way. So he asked the question whether every row invariant section of a Deligne-Hitchin moduli space is given by a solution of a self-duality equation. So it turns out that the answer is no. So we have found some counterexamples. So there exist sections of this moduli space, of the Deligne-Hitchin moduli space, which are invariant under the real involution rho, but they are not corresponding to solutions of the self-duality equations. This is joint work with Indranil Biswas and Markus Röser from Hanover. And because I somehow like that result, I proved it a second time together with Lynn Heller, also from Hanover. But in the second theorem, we produced somehow other sections of that Deligne-Hitchin moduli space. And these sections turn out to solve the self-duality equations on an open and dense subset of the Riemann surface, but not on the whole Riemann surface. So let me describe somehow how we obtained this result here and how to distinguish these sections and those sections here. So in order to do that, I need to discuss lifts of sections of the Deligne-Hitchin moduli space. What I mean by a lift is a family of flat connections of the following form. So they are parameterized by C star, by the multiplicative group, and have the following asymptotic at lambda 0. So there's basically a Higgs field at lambda 0 showing up. So if I want, I can rewrite that as a section of the space of lambda connections, not of the moduli space. So it's just a lift from the moduli space obtained by factoring out the gauge group to the actual space of lambda connections, which is of course an infinite dimensional space. If we have such a lift for a real and irreducible section, what we have from the reality condition is that the connection at the point minus lambda bar inverse is gauge equivalent to the connection at the point lambda by some gauge transformation, which depends holomorphically on that spectral parameter lambda and can be chosen to be a family of S2C gauge transformations. And then applying this identity twice, we obtain, under the additional assumption that we are having irreducible connections, the following formula, namely the product of these gauge transformations must be either plus or minus identity. And it's not hard to see that this sign here is an invariant of the section. So whatever lift we take, the family of gauge transformations corresponding to that lift will give us the same sign, just depending on the kind of sections we are dealing with. And as an example, for the twistor lines, so for solutions of the self-duality equations, we get a minus sign because this gauge transformation is given but constantly by this off-diagonal guy here. So how I'm sorry? The dot? It expands in lambda. Yes, right. I'm sorry, I forgot. So it can have infinitely many terms, but the condition is that these connections are all flat for all lambda. But in order to describe how we have obtained counterexamples, let me briefly recall how harmonic maps into the round free sphere or into the group SU2 can be described. So if we have a harmonic map from a Riemann surface X into that space, we have the induced connection of this round free sphere and an induced spin connection, and we can pull it back to our Riemann surface and consider the basically 1/2 of the complex linear part of the differential or of the Maurer-Cartan differential of our harmonic map. And then this automatically satisfies a certain kind of Gauss-Codazzi equation and a holomorphicity equation if and only if the map F is harmonic. So this almost looks like the self-duality equations with the difference that we have a different sign here, and the difference of that sign can be seen either from, that this free sphere has positive curvature via hyperbolic space corresponding to the solutions of the self-duality equations has constant negative curvature. But from the point of view of the Deligne-Hitchin moduli space, what we get for a harmonic into the round free sphere is a section. Just take the associated family of flat connections, and this section of the Deligne-Hitchin moduli space is also real, but now with respect to the complex structure C, which differs by the complex structure rho by this minus sign. And the idea is now the following. So if we start with harmonic maps which map into a totally geodesic two sphere, it was already observed by Hitching that they satisfy the additional symmetry, that they are basically invariant under taking its negative. So what that means is that we should study those examples. But the bad thing here is, of course, that these sections will go through reducible points automatically, because we have started with a harmonic map into the two sphere, which has no holonomy or no monodromy, which means that the connection must be trivial at certain points. Lambda is 1 and -1. So we want to do better and construct sections which only go through the irreducible points. So what we do is the following. We start with a stable holomorphic structure which admits a nilpotent Higgs field phi. So those certainly exist. And what we do then is we scale phi to be very small. And if this happens, it turns out that there's a unique solution of the harmonic map equation. And in other words, this means that if phi is very small, then we have a family of flat connections, nabla lambda, of the form nabla plus lambda inverse phi, and now minus lambda phi star. And this family is not invariant under n so far, but we can make it invariant by a transformation which might be called Gauss map, because it corresponds to a certain identification of harmonic maps in the free sphere. So if we consider minimal surface in the free sphere, they are given by harmonic maps which are conformally parametrized. And conformally parametrized just means that we have a nilpotent Higgs field. Then it turns out that these minimal surfaces can be characterized by the fact that their Gauss map, so their normal when trivialized into the two sphere, is also harmonic. And this gives us an idea how to make an appropriate section out of the section we have here. Namely, we do some kind of thing which we call twisting. So because phi is nilpotent, we have a kernel bundle. Let me denote it by L. We take the rank 2 bundle to be the topological decomposition of L plus its dual. And with respect to that, we consider the new family, nabla tilde lambda, which is given by nabla squared, times a gauge transformation, h of lambda, which looks like, and I think this is true, 1 over lambda and square root of 1 over square root of lambda and square root of lambda with respect to the decomposition L plus L dual. So, of course, this, if I take the square, I wouldn't get a section, and these gauge transformations are not well defined in lambda, but have that square root problem. But this new family of flat connection turns out to really give me a nice section of a Deligne-Hitchin moduli space, which is invariant under this n, which is, if we start with a small Higgs field, which only goes through irreducible points, and it turns out to be a real section with respect to rho. And if one does a short computation, one sees that this section has a plus sign in the equation 1. So it has a plus here, and this just means that it must be different to a solution of a self-duality equation. And in that way, we obtained counterexamples. So, having observed that it's possible to describe other kinds of harmonic maps than harmonic maps into the hyperbolic free space by the Deligne-Hitchin moduli space, one can ask the question, what else can we do? And so besides the hyperbolic free space, oh, that's of course a misprint here, and besides harmonic maps or equivalent harmonic maps into a hyperbolic free space or harmonic maps into SE2, what we can get is the following two possibilities. So the first consists of a space of oriented circles in the round 2 sphere, which can be described by SL2C mod SL2R. And then harmonic maps into that space basically correspond to real holomorphic sections of a Deligne-Hitchin moduli space with respect to rho, which have a plus sign in the equation 1. And a particular example of that is, of course, our counterexample to the question of Simpson. Namely, what we have produced is basically an equivariant harmonic map into the round 2 sphere, but the round 2 sphere naturally sits in the space of oriented circles in the 2 sphere by just looking at great circles. So this counterexample can be considered as this equivariant harmonic map into the round of into the space of oriented circles in the 2 sphere. Another example which is very interesting is the anti-de Sitter free space identified with SL2R, where we have a quadratic form given by minus the determinant. And then these harmonic maps into ADS3 basically correspond to real positive sections with respect to n circ rho, so with respect to the complex antiholomorphic structure C, and not with respect to the one corresponding to the twistor space. The example or the counterexample can be generalized, so we can observe that real sections with respect to the antiholomorphic involution rho, which are invariant under n, are automatically n circ rho real sections, and vice versa. And if we do that, what we obtain is that n automatically interchanges the positivity and negativity of sections. So another example, which besides these counterexamples, which is quite nice to consider, are these twistor sections or solutions of the safety equations whose associated sections are invariant under n. And it was already computed by Hitching that those are either given by zero Higgs field or components of what is now known as a Hitching component. And if we do that, we get the following theorem, again with Indranil Biswas and Markus Röser, that the Toledo invariant of such an element of the Hitching component is given by a certain degree of the section corresponding to of the corresponding n circ rho real section. So what is that degree like? So let me shortly explain that. So we have a family of flat connections of the form lambda inverse phi plus nabla plus lambda psi. And what we have is the reality condition so in that situation, if we only have these three terms in the expansion, what we get is that this gauge transformation can be chosen to be constant. And then G times G star, G times G bar is, under the positivity, automatically the identity. So what we get from that real section is a map G, which satisfies the equation G times G star to be the identity. And this space is again isomorphic to the space of oriented circles in the 2 sphere, and as such it has a degree because its deformation retracts to the sphere. So this degree of a section can be defined for all positive n circ rho real sections, and is a natural generalization of the Toledo invariant for elements of the Hitching component. So another theorem which can be obtained from the point of transformation between these sections is that these elements of the Hitching component give rise to equivariant and possibly branched minimal surfaces in the anti-de Sitter free space. So this was certainly observed by physicists 10, 20 years ago, but locally. But now we can interpret that globally on compact Riemann surfaces as some kind of nice correspondence between certain kinds of sections of the Deligne-Hitchin moduli space. Yeah, it has Lorentz metric. It has Lorentz, yes. Yes. So these sections we have considered so far are basically, or we have seen so far, are basically quite easy sections. So in the twistor setup, they are just constant, certainly on in the first component, and the other sections I try to describe here are just variations of them. So it looks like there are only these basic kind of sections. But let me explain that one should expect that there are much more complicated sections which also give rise to interesting phenomena. In order to do so, I want to start with harmonic maps from a torus now. So I restrict to genus 1 for a second to the round free sphere, so to SU2 before. And again, we have this family of flat connections. And because a torus has, of course, a abelian fundamental group, we have a decomposition of a generic flat connection on a rank 2 torus into direct sum of parallel connections on line bundles. So if we want to describe families of flat connections, what we do, families of flat SL2C connections or gauge classes of families of SL2C connections, what we can do is we could try to parameterize the families of line bundle connections. But of course, at certain spectral points, these line bundle connections can come together. And what we need is a double covering in order to be able to parameterize these line bundle or gauge classes of line bundle connections. So the moduli space MDR C star denotes the Dirac moduli space of flat line bundle connections. In that setup, Hitchin has proven that this curve parameterizing these line bundle connections can actually be compactified by adding points over 0 and infinity, and then the map D into the space of line bundle connections is basically given algebraically. So it can be described by an odd map into the affine bundle of flat line bundles over the Jacobian of the initial torus, which has a certain kind of pole of order 1 over point 0 and similar behavior at infinity. And from the point of view of this Deligne-Hitchin moduli space, we could consider this map D as a special odd map into the C star Deligne-Hitchin moduli space, but now not from, it's not a section, but a map covering a spectral curve. Yeah, because of the geometric origin, this map satisfies certain reality condition, and this means that all the informations are basically contained in the map into the projection into the Jacobian. So we just need to look at the map into the Jacobian in order to recover the flat connections. And because this construction basically has factored out the gauge group, so we just look at the gauge classes, one needs to ask if we can go back, and it turns out we can go back by taking some additional information, the so-called eigenline bundle. And if we do that, we fix the gauge freedom, and one can reconstruct harmonic maps explicitly in these algebraic geometric data, the spectral curve, this map D, and the eigenline bundle. And this reconstruction turns out to be basically a particular instance of a Hitching system. So let me just show some pictures produced by Nicolas Schmidt, which show constant mean curvature tori. So constant mean curvature torus is a surface minimizing or being a critical point of the area with fixed enclosed volume. But they are characterized by the fact that their Gauss map, their normal, is harmonic. So what you see here basically is how complicated the corresponding harmonic map is. And it turns out if you start with spectral curves, sigma, which is of spectral genus 0, these surfaces are quite easy, they're homogeneous. And the more complicated the spectral curve gets, so the higher the spectral genus gets, the more complicated the surface gets. So this has spectral genus 1, for example, and I think this has spectral genus 6 or so. So you basically see that the more complicated the spectral curve and the corresponding map into the Deligne-Hitchin moduli space is, the more complicated the harmonic map gets. The same can be somehow be done for higher genus surfaces, at least for harmonic maps which are in a certain sense close enough to tori. In a sense I don't want to explain, but I just want to give you some kind of picture. So these are CMC surfaces which correspond to somehow easy sections of a Deligne-Hitchin moduli space. And here, these more complicated surfaces correspond to more complicated sections in the Deligne-Hitchin moduli space. And the more complicated those sections get, the more complicated our surface, or our CMC surface, or our harmonic map gets. There is actually some kind of invariant which tells how complex that Deligne-Hitchin map is. Namely, if we remember that the associated family of flat connections, or if we see or observe that the associated family of flat connections of a harmonic map into SE2 has only unitary connections along the unit circle, then by Arashima-Seychart just means that all the holomorphic structures on the unit circles must be stable or semi-stable. And here what we have is that the more complicated we get, or the more bubbles we have on each leg of the surface, the more unstable holomorphic structures sit inside the unit disk. So this is certainly some kind of invariant measuring how complicated our section gets. So let me end the talk by just saying a few words about what these higher solutions of Hitchin's F2 equations are or should be. So what I tried to explain in the last few slides is that it's sometimes possible to put certain kind of bubbles on harmonic maps into the free sphere. So, for example, we have seen that for these tori, that one just needs to consider high spectral genus to get more and more bubbles on the surface. For harmonic maps into H free, so in a hyperbolic free space corresponding to the Self-duality equations, this is not possible. So one can see it either from the fact that the Higgs field or the Higgs pair already determines the harmonic map uniquely, or one can try to give some kind of heuristic arguments, either that one should observe that these bubbles somehow correspond to reducible connections in the associated family of flat connections, or because of the more analytic observation that there are no compact minimal surfaces in the hyperbolic free space. But what we do get is some kind of minimal spheres in the hyperbolic free space, which go through the boundary at infinity in a very nice way. So let me draw the ball model of a hyperbolic free space. And you see here the boundary at infinity. But outside, there's a second copy of the hyperbolic free space. And if I just take a plane, if I just take a plane, this goes through infinity, of course, but this plane gives me some kind of a minimal sphere in the hyperbolic free space, which goes through infinity. And this should somehow correspond to what bubbles for these self-duality equations should be like. They automatically go through infinity. So these higher solutions of Hitchin self-duality equations are solutions of self-duality equations which are defined in an open dense subset of the Riemann surface, which go transversely through the boundary at infinity, like this minimal sphere. And of course, they should also give real sections of the Deligne-Hitchin moduli space. And the existence of such solutions was proven in the second theorem I mentioned in my talk. So thank you for your attention. Yes. Okay, I think this is a very good question. So I think the first counterexamples are some kind of exceptional, because this is based on a particular symmetry in low dimensions. But these other higher sections or these higher solutions, I think this is some kind of general phenomena that there are more and more complicated sections of these twistor spaces which should exist in every rank. And of course, it would be a nice task to compute whether these connected components of such kind of sections also give us, for example, a nice smooth manifold with maybe a hyper-Kahler structure. So of course we are looking for that, but so far we haven't done anything into that direction. Yeah. I don't really know. I'm sorry, but I guess here are some experts in that which might know. So, yeah. Okay, I haven't really explained that. I actually was invited to give another talk next week in Mumbai, where I will somehow explain how to go from these more complicated sections for tori towards these higher genus surfaces. But this is nothing which is very easy to explain, and it would take a while. But maybe after the talk, if you are interested, I would be happy to explain more.